Good. So, dear participants of Cal Data Science School, let's continue. The break is over, and now we're starting the second lecture of today. It is called Machine Learning for Neutrino Physics Experiment and is brought to you by Dr. Olga Gogota. She has a PhD in physics of the nucleus, elementary particles, and high energies, and she is currently a researcher at Taras Shevchenko National University of Kyiv. So, Dr. Gogota, good afternoon to you.
Good afternoon.
Yes, so a quick reminder of our housekeeping rules. Please have your microphones off. You should not be able to turn them on, but in case you can, just don't do that. And all of the questions are collected in written form using Slido. So please follow the QR code that you see right now and to open it, or I'll just share a link to the same Slido instance in our chat in a minute or two. Yes, so that's it from me. So, Dr. Hodota, the stage is yours. I'm here on the background, letting everyone in from the waiting room.
Yes, thank you. Okay, thanks. First of all, I would like to thank you for this opportunity to give a talk on Cal Data Science School 2024. And today we are talking about using of machine learning for neutrino physics experiments. You can see the brief outlook of my talk. Today we will talk about basics of neutrino physics, some kind of crash course in particle physics actually, the reasons to use the machine learning in the analysis of the data from neutrino experiments, and some examples of using machine learning algorithms for different tasks. And the last one, the problems and benefits from machine learning in neutrino physics. So we are starting actually from the beginning, from the standard model of particle physics. As you maybe remember or know, or maybe hear, the standard model of particle physics is the theory that describes the behavior of elementary particles and their interactions. It's a quantum field theory that classifies all known elementary particles, and it includes three fundamental forces of nature: electromagnetic, weak, and strong interactions. But it does not include gravity. This model was developed throughout the latter half of the 20th century and has been confirmed by numerous experiments. For example, the discovery of the Higgs bosons in 2012 at the Large Hadron Collider. The standard model consists of three families, as you can see, of elementary particles: leptons, quarks, and bosons. Leptons include electrons, muons, and taus, and corresponding them neutrino, while quarks are divided into up, down, strange charm, bottom, and top quarks. Bosons, which are here, are the particles that mediate the fundamental forces, such as photons for electromagnetic interactions, W and Z bosons for weak interactions, and gluons for the strong interactions. The standard model has several shortcomings, including the need for 19 arbitrary parameters, inability to explain the origin of lepton and quark masses, and violation of symmetry known as SCP violation. And it can explain the dark matter, dark energy, and, as I mentioned before, gravity. Despite these limitations, it is considered one of the most successful scientific theories for all time and serves this as the foundation for further research in particle physics. So, returning to neutrinos, they are the only fundamental fermions that without no electric charge. They only interact through the weak force. And according to the standard models, they are massless. And there is a list of questions which the standard model can't explain or answer. And neutrino physics experiments actually is looking for answers for this question. It's, for example, how much this neutrino weight, which neutrino is the lightest, how many flavors of neutrino are there, and so on. Okay, in the standard model of particle physics, neutrinos belong to the lepton family and have 3 flavors. It's electron flavor, muon flavor, and tau flavor. As I mentioned before, they do not have electric charge and they are leptons. They are always so-called left-handed particles, while antineutrinos or their antiparticles always right-handed. But they can change this flavor. And this process is called oscillation. Oscillation between flavors over the time, and therefore they have a mass. As we mentioned before, the standard model said that neutrinos does not have a mass. And the 3 mass states are a superposition of these 3 flavor states of electron flavor, muon flavor, and tau flavor. What are others questions about neutrinos, what we are looking for in the experiments? Which one neutrino is the lightest, and do neutrino and their antiparticles behave in the same? For this question, we study neutrino oscillations at different experiments. Another part of a difficult question for the standard model is what's absolute mass scale for the neutrinos? Actually, how do neutrinos get their mass? And for these questions, there are experiments which study neutrinoless double beta decay, which are direct mass searchers. And all of these questions can be answered thanks to studies in cosmology. Okay, there are a lot of different particles, and how do we detect all of them? For photons energy, we are using photomultiplier tubes and silicon photomultipliers. When we are talking about the charged particles, what we can say that they produce light in scintillators that we can gather, and they can ionize some matter, for example, liquid argon in time projection chambers. As if I remember, neutrino interacts weakly, and we can detect them only if they interact with the matter of the detection volume. What we want actually to know about oscillations or changing type of neutrinos. We know to know the probability of a neutrino oscillation as a function of its so-called true energy. But what we at the experiments measure? We measure oscillated neutrinos as a function of measured energy. Generally speaking, there are two big groups of neutrino experiments, which divided in accelerator neutrinos experiments and reactor neutrinos experiments. Reactor neutrino experiments catch the neutrinos from the nuclear plant's reactor and have some detection volume. When we are talking about accelerator neutrinos experiments, we have some acceleration facilities for the neutrinos. On this plot, you can see the diagram and sensitivity to the parameter which characterizes the oscillation of neutrino and what kind of detection volume are using for now in different experiments. It's a plastic scintillator, emulsion, water or ice, a liquid argon, liquid scintillator, magnetized iron, and even gazonic argon. Coming back to using of liquid argon as a detection volume. On this plot, you can see that there is a whole family of LAR-TPC or liquid argon time projection chambers experiments, such as Microboon, Icarus, SNB&D, and future experiments, DUNE, Deep Underground Neutrino experiments. LAR-TPC are used in neutrino experiments due to their high electronegativity, which make them transparent to the slow-moving electrons produced by the neutrino interaction. So we have a neutrino, goes through the volume, and neutrino interacts with the argons. When a neutrino interacts with argon atom, it creates a high-energy charge lepton, which ionizes other argon atoms as it passes through the liquid, leaving a trail of free electrons and argon ions in its wake. The electrons are drawn into the wires by the strong electric field and register as a pulse of current in a particular wire. The position of the heat wire and the drift time of the electrons are combined and provide us, scientists, a 3D reconstruction of the event. The big advantages of liquid argon time projection chambers include their high precision and low energy threshold, which allow us for highly detailed reconstruction of the neutrino events. But they cannot be made as large as water Cherenkov detectors, and their high precision can be traded off against a smaller sample size. Liquid argon detectors are also good scintillators, and their scintillation properties are important for detecting and reconstruction neutrinos events also. The next experiments that we will be talking about is NOVA experiment. This experiment used liquid scintillator. The NOVA neutrino experiment is a long baseline neutrino oscillation experiment that aims to measure the appearance of electron neutrinos in a beam of the muon neutrinos produced by the NUMI beamline at Fermilab. The experiment used two detectors, one at Fermilab, so-called near detector, and one is northern Minnesota, so-called far detector. And the distance between all these two detectors is 800 kilometers. The primary goal of this experiment is to measure three-flavor neutrino oscillations and to study the oscillation properties of neutrinos, which are not predicted by the standard model of particle physics. When a neutrino strikes an atom in the liquid scintillator, it releases a burst of charged particles. As these particles come to rest in the detector, their energy is collected using wavelength shifting fibers connected to the photodetectors. Using the pattern of light seen by the photodetectors, we can determine what kind of neutrino caused this interaction and what it has energy. One more experiments also situated at Fermi National Laboratory in the United States, it's Minerva, main injector neutrino experiment to study neutrino nucleus interactions. It was designed to study neutrino interactions with different nuclei using a high-intensity neutrino beam. It was the first experiment in the world to use this high-intensity beam to study neutrino reactions with 5 different nuclei, providing high-precision measurements of neutrino interactions in the energy range from 1 to 10 GeV. The results of these experiments are crucial for understanding neutrino oscillations and the structure of protons and neutrons, shedding light on the forces governing neutrino nuclear interactions. Minerva research has covered a wide range of topics related to neutrino interactions, including neutrino flux measurements, charge current, quasi-like reactions, productions of pions and kaons, and so more. This experiment has provided valuable insights into neutrino interactions and has contributed significantly to the field to neutrino physics. Two more examples for different experiments. The next one is so-called Kaplan-Zenz experiment, and is a scientific endeavor aimed to detect neutrinoless double beta decay of the xenon nuclei. If these processes will be observed, it will provide significant insights into the nature of neutrinos, particularly whether they are Majorana particles, meaning that neutrinos are their own antiparticles. The experiment utilized a large volume of liquid scintillator detector Kamland, which contains almost 400 kilograms of enriched xenons. Another one example of a different structure of experiments is the Ice Cube Neutrino Observatory. This experiments located at the Amundsen Scott South Pole Station in Antarctica. It's designed to detect neutrinos, which are nearly massless and chargeless subatomic particles and rarely interact with matter. Ice Cube covers a cubic kilometer of ice and utilizes the Antarctic ice as its detection volume. The observatory consists of thousands so-called digital optical modules, or domes distributed over strings, which are buried deep with the ice at depths ranging up to almost 2.5 kilometers. The primary goal of this experiment is to observe high-energy neutrinos from astrophysical sources, such as exploding stars, gamma-ray bursts, and phenomena involving black holes and neutrino stars. By detecting these neutrinos, IceCube aims to answer a fundamental question in physics, including the nature of dark matter and the properties of neutrinos themselves. It also observes cosmic rays that interact with the Earth's atmosphere, revealing structures that are not yet understood. The domes, or digital optical modules in IceCube, detect neutrinos through the Cherenkov radiation emitted when neutrinos interact with the ice, creating charged particles that move faster than light in the ice. This radiation is then captured by the domes, allowing scientists to reconstruct the energy and direction of the incoming neutrinos. It's not full list of neutrino experiments, but it gives the range of possible experimental setup for searchers in the neutrino sector. Different experiments give us an opportunity to see a wide range of neutrino energy. For example, nova experiments look for an energy of neutrino up to 5 GeV. GeV is a unit of energy. It is defined as the amount of kinetic energy gained or lost by a single electron when it's accelerated through the electric potential difference of 1 volt. And in particle physics, the energy usually presents in such units. Another experiment, Catherine, which is trying to determine the absolute mass of neutrinos, is looking for a tiny, tiny difference, shown on this plot on the right hand, and the order of these searches is 1 eV. At the same time, IceCube, as we described on previous slides, can detect neutrinos with the energy up to 2 PeV. Such a big range of experiments and neutrino energies, what are we looking for? Give us a great range of different topologies. Just compare the displays for nova experiments, microburn, IceCube, and next. If you are talking about nova experiment, the scale is few meters. If we talking about the microburn experiments, you can say that it's 7-10 centimeters. For IceCube, it's not few meters, it's almost 100 meters. And for neutrinoless double beta decay in the next experiment, we operate in the units just few centimeters, even millimeters. Neutrinos are very interesting particles to study about them, and you can see that the experimental setup is very different and allow us to make absolutely different studies. It was the first part of the talk, mostly of the physics, but why machine learning actually? First of all, neutrino experiments will have, as Dune experiments, in huge data sets. Another reason that traditional analysis methods are limited by their complexity. Also, machine learners are good at handling of high-dimensional data. And it's a good point that we can identify hidden pattern and correlations thanks to machine learning. As you far remember about how we collect data from the detector, for example, for liquid argon time projection chambers. The data collected by neutrino detectors can be represented as 2D or 3D images, where each pixel or voxel corresponds to the energy deposition or light signal from a neutrino interaction. This image-like structure makes, for example, computer vision algorithms well suited for analyzing neutrino data. One more reason to use machine learning is pattern recognition. Neutrino interactions can produce complex particle trajectories and energy deposition patterns within the detectors. Convolutional neural networks excel at recognizing intricate patterns in image data, making them available for identifying and classifying different types of neutrino interactions. From the technical side, for the last 20 years, there is a huge growth in computer power over the last decade. But particularly, I mean GPU technology. And at the same time, networks are becoming much more accurate whilst requiring fewer computing resources. There are a lot of tasks for machine learning in neutrino experiments. The simple one is the classification tasks. For example, binary classification, I mean on signal events and background events. A more complicated task is non-binary classification. The next one, what will be talking about is a regression task when we want to know, for example, energy of neutrino, angle or coordinate of the interaction point or vertices. The next one is object recognition. Neutrino physics, it pertains to the detection and analysis of neutrino interaction events. Close to this task is a segmentation task when we want to predict a class of particle at the pixels level. Graphs usually are used when the classical deep neural networks or convolutional neural networks can be applied or have not satisfying metrics. All of these things in general can be used in real time. This usage has shorter histories, for example, some LHC experiments, but have a huge potential in the future. And the last one, as a task for machine learning applications in neutrino physics, is using of generative networks for event generation instead of Monte Carlo data. It's need to decrease the time of generating of Monte Carlo data and so on. Okay, the first using of artificial neural networks in neutrino physics was done in 1995, 1996 by Snow experiments. It was just binary classification. It classified events using heat patterns, and at that time, they don't achieve much better metrics than general algorithms, but this work showed that it's possible to use machine learning algorithms in the neutrino physics and explore these techniques in the future. As an example of the regression task, I mean the vertex in the energy reconstruction, Juno experiments used few architecture. Actually, it's where boosted decision trees, deep neural networks, a few kind of convolutional neural networks, which are based on ResNet and VGG, and graph neural network based on deep sphere. This experiment, generally speaking, is a multi-purpose neutrino experiment that aims to address several questions in neutrino physics. It's also a liquid scintillator detector, and it is a medium baseline reactor neutrino experiment. The main physics goals of these experiments is determination of the neutrino mass hierarchy, which is one of the fundamental open questions in the neutrino physics. By observing these antineutrinos, this experiment aims to determine the neutrino mass hierarchy at 3 sigma significance with 6 years of running. In addition to its primary goal, Juno has the capability to observe neutrinos from various terrestrial and extraterrestrial sources, including supernova burst neutrinos, diffuse supernova neutrino background, atmospheric neutrinos, or even solar neutrinos. Comparison all these few architecture, they have a good resolution for energy in 3%, for visible energy of 1 MeV, and for the position of the vertex, they have about 10 centimeters of resolution. The example of the object recognition is published results of microburn experiments in 2017. And they show that AlexNet plus faster recursive convolutional neural network model can successfully learn neutrino interaction features and localize them in an event view. On the left side, you can see just the simulated neutrino interaction with a bounded box that were using for training. And the same event on the right hand that overlaid with data, real data from the cosmic. And this bounding box is used to train the detection network layer. The next one example is a few examples of gross neural networks that were using by different collaborations and experiments. As you remember, Ice Cube is the experiment suited in the ice, and it has not uniform detectors, which takes data that is very sparse. And actually, it's not well suited for convolutional neural networks. The input data to this graph neural network is an event that consists of n digital optical modulus represented as a graph vertices. So vertex of our graph is domes. To each input vertex, we have a six-dimensional feature vector, which is associated containing x, y, z position of its corresponding digital optical modulus as the sum of charge in the first pulse with the sensor and the time at which the first pulse crosses the activation threshold. The task for these graph neural networks is to classify event into positive neutrino events or negative backgrounds. A typical event activates only a sparse set of digital optical modules. The graph neural networks architecture naturally allows to handle such situations by ignoring the inactive vertices, considering graphs of different size. What about the graph construction? The geometry of the detector is represented by a fixed, weighted, and directed graph. The weights are defined only by the special positions X, Y, Z of the digital optical modules. Architecture is involved the convolution part and also pooling. And these graph neural networks identifies 600% more signal events than a convolutional neural network or traditional algorithm with a signal-to-noise ratio, which is 3 times larger. You can see the table with the signal-to-noise ratio. Another example of using graph neural networks, but on this time for liquid argon time projection chambers, it's work of the collaboration of ExaTIR-KX, and they have recently submitted to the arXiv the paper. What can stand for their studies? That RTPC hits can be connected in a graph, naturally, and it's a naturally sparse representation of the data. And this is These are low-level information, close to native output of the detector. And graphs can also connect hits from different planes. Those makes the network 3D aware. Main inputs to the graph neural networks from this collaboration are the hits. As you remember, for IceCube, it was special dimensions of digital optical modules. And his associations to 3D space points currently from SP-solver algorithms are used to create nexus connections across the graphs in each plane. These graph neural networks, new graphs too, originally is for semantic hit classification. So we have a hit and want to know to what of classes it belongs. For their work, Exoterics collaboration use 5 semantic categories, such as minimum ionizing particles, S-muons or charged pions, highly ionizing particles. This is protons, electromagnetic showers, Michel electrons, and diffuse activity. We can see the efficiency of this network, and what we have that it efficiently rejects backgrounds. Detector hits classify detector hits according to particle type, and this network is lightweight network, allowing fast inference on CPU and GPU. And another point that the next step, this collaboration have a very promising results for vertexing or vertex position. The next one example is segmentation. The task is to predict a class of particle at pixels level. The labels in the data set for supervised learning include 5 possible classes. These 5 classes is similar to previous one, but there's we have the last one is delta rays. There are a lot of works that using open dataset pillar nets. So the work starting on 2019, 18, and still different collective of authors published on them to improve the results. And the base of first work, it was URSNet, classic architecture with special submanifold sparse convolutional networks, which have been proposed to address this class of challenges. In other subsequent works, different authors have improved their values for the mid-share electron reconstruction using different methods. For example, adding a self-attention block, modifying networks, and etc. we have also published some results in Ukrainian journal with this using of attention block with URSNet and modified version of URSNet 3 plus architecture. And it's a very huge benefit that this can be done on the open data set, as neutrino experiments are in no hurry to make large data sets as public. What about real-time machine learning? It includes triggering, just recently there were a work with the name that 2 watts is all you need, enabling in detector real-time machine learning for neutrino telescopes via edge computing. In the forthcoming years, there is an anticipation of upgrades to existing detectors and the introduction of new telescopes featuring innovative experimental hardware. This is expected to generate more extensive data statistics and increasingly intricate data signals. This study represents the initial endeavor and proof of concept towards enabling the deployment of machine learning techniques within detectors for water or ice neutrino telescopes, achieved through quantization and deployment on Google Edge Tensor Processing Units, or TPUs. The authors devised a recursive neural network featuring a residual convolutional embedding and employed a quantization process to implement the algorithm on a Google Edge TPU. This algorithm demonstrates comparable reconstruction accuracy to traditional GPU-based machine learning solutions while consuming a similar amount of power to CPU-based regression solutions. This amalgamation of high accuracy and low power consumption enables real-time machine learning within detectors, even the most power-constrained environments. Also, for example, the Dune experiment have published results on PUFAR detector in 2020s, and the same architecture was embedded to FPGAs on 2021-22. And the last one, example of using of machine learning for neutrino experiments is event generation, also based on liquid argon time projection chamber samples. And this paper presents work towards a generative model which can produce convincing RTPC images. This is the first demonstration of a generative network that produces shower trajectories at the first without underlying physics-based model. The model produced patterns that do resemble track and shower trajectories, but there is clear need for improvement. Preliminary features at larger scales are difficult for this network. Authors plans to move towards conditional generation where the particle spaces and momenta can be specified. This gets them closer towards applying these models to event reconstruction. The types of features found in the liquid argon time projection chambers image have different natures than the common data sets that the machine learning community develops on. This should make LARTPC images an interesting data set for studying different approaches in generative modeling. Okay, but what kind of problem we have using of machine learning in our measurements. First of all, it's the large backgrounds. Neutrino experiments often face large backgrounds, which can make it challenging to distinguish between neutrino interactions and other particles. Machine learning algorithms can help in identifying these backgrounds and improving to the signal-to-noise ratio. Another problem, they are elusive signals. Neutrinos are weakly interacting particles, making them difficult to detect directly. Machine learning can help in reconstructing the interactions and identifying neutrinos in the data. Also, we faced too small statistics. And these small statistics can limit the accuracy of the measurements. Machine learning can help to extract more information from the limited data available. Another problem that we have for different experimental setup, it's non-regular geometry and sparsity. The data from neutrino experiments can have non-regular geometry and be sparse, which can make it challenging for algorithms of machine learning to learn the underlying patterns. High dimensionality. The data from neutrino experiments can be high dimensional, which can make it challenging for algorithms to learn the underlying patterns. Scalability. Machine learning algorithms can struggle to scale to the large data sets and complex systems. Use the next generation neutrino experiments, such as Dune experiments. Another, up to me, a big question and problem is uncertainty estimation. Traditional uncertainty propagation may not capture the uncertainties inherent in machine learning models, which can make it challenging to estimate the reliability of the predictions. And machine learning can be difficult to interpret and explain, which can make it challenging for, first of all, physicists to understand the physics and make decisions based on the results of machine learning algorithms. And the last one is open data sets. For now, I know just 3 open data sets that we can The first one is KME3NetT collaboration provides open access to data from its neutrino telescope, which registers neutrino from both astrophysical sources and atmospheric interactions. This initiative aims to support a wide range of scientific research in astroparticle physics, marine science, and beyond. The data are made available through the internet interfaces, along with tools, procedures, and even documentation developed to facilitate their use. Another one, the microboon experiment at Fermilab has released a dataset divided into 2 parts for the public. These datasets contain simulated neutrino interactions from the booster neutrino beamline, overlaid on top of cosmic ray data collected with the microboon detector. The data is provided in a format suitable for a broad audience. As far as I remember, it's H5 format, as well as for users familiar with the software infrastructure of Fermilab neutrino experiments. This initiative allows users to freely reuse the data with the requirement of giving appropriate credit to the collaborations. And another one is mentioned before, PillarNet, which describes large TPC data. To address these challenges, researchers are developing new machine learning techniques and algorithms specifically tailored to the need of neutrino physics. This includes the use of generative models, diffusion models, and deep learning network for data analysis and reconstruction tasks. Additionally, there is a growing focus on uncertainty measurement and estimation to ensure that reliability and physical meaningfulness of the machine learning models used in neutrino physics. By incorporating machine learning into neutrino physics experiments, we can achieve several obviously benefits. We can improve signal-to-noise ratio, allowing us to isolate the faint neutrino signals from the background noise more effectively. This enhanced sensitivity allows us to detect rare neutrino processes that were previously undetectable. Additionally, machine learning can automate the analysis processes, freeing up researchers' time for more complex tasks. Ultimately, the use of machine learning can lead to groundbreaking discoveries in our understanding of neutrinos and the universe. What we expect in the future of neutrino physics within the machine learning? We can expect new and more powerful machine learning algorithms. Integration of these algorithms to next generation neutrino experiments. Again, new insights into neutrino properties and advancing our understanding of the universe. And this talk was prepared based on our overview paper on machine learning in neutrino physics, which was submitted to the Journal of Physical Studies. It's Ukrainian journal in Lviv. Thank you for your attention.
Yes, Dr. Gogota, thank you very much for such an interesting lecture. Just sitting here from a complete mathematical computer science background, it was like for me personally very interesting to see how the stuff that I've learned just like theoretically and that I've been learning to just some apply to other problems, how these same algorithms have found great usage in like a completely other field and how this field benefits from it. So, and it wasn't interesting only for me. We do have a couple of questions. So please let me share my screen now in just a moment. Mm-hmm. Okay, so I'm going to read them out loud and then you will answer. So the first one is regarding, I guess, regarding the model PillarNet 2020. What is the 3D space on the left graph? Is it after some kind of dimensionality reduction? And do you have ground truth for these labels?
Okay, maybe it's better to
Yeah, so let me
share.
stop sharing. You will reshare to show the slide to the audience.
Okay, and it was PillarNet,
Yes, 2020.
the left side.
Yeah, what is this 3D space? Is it after some kind of dimensionality reduction? And are there any ground truths for these labels?
It's definitely ground truth labels because we are working with so-called Monte Carlo data. PillarNet dataset is Monte Carlo data based on the Joint for simulation, and neutrino generators. We have these labels for each pixels. And on the right hand, the cyan is the work of these semantic segmentation algorithms.
Okay, thank you very
Does
much.
it covers? Okay.
Yes, you just said, and yes, the 3D space on the left. Is your data three-dimensional, or it was a bigger dimension before the start?
It's three-dimensional.
Okay, so
And this data set have a few sets of pixels, I mean 192 by 192 by 192, and the biggest one is 768 by 688 by 688. We have these data sets in 2D and in 3D.
okay, thank you very much. So
Some kind of pictures,
there are
actually,
other
images.
questions about neural networks, so I guess I will read them right now and you will keep the screen shared. So the next question is about IceCube 2018. Why is sparse data not suitable for CNNs? What does sparsity mean in that particular context? So yeah,
About parsing, okay. It's maybe the best picture. What I mean is sparsing for the data. It's pictures for natural current and charge current for neutrino events.
Mm-hmm.
As you can see, in one place we have like a huge balls, and another volume it will be really with zeros. It is some kind the same problem with large TPC images, that in one place we have a lot of pixels that we need to study, to investigate, to give them a label, but in 2 meters, we have nothing. And the next generation experiments like Dune will be modulated in modules. We will have 40 tons of liquid argons. And if you put the image of such big detectors of 40 kilotons of liquid scintillator, it will be hard for algorithms to calculate all these 0 pixels at large TPC detectors and in the representations for IceCube detectors, where they used digital optical modules and information from them. So they decided to go through the graph, and it's the key point. What
Right.
another part was of this question?
Yeah, it was about what sparsity means in that context, and why sparse data was bad for CNNs, convolutional neural networks.
There were trouble with the convolutional parts without graphs.
Mm-hmm.
I do not remember exactly what kind, but really it was some problem with convolutional in general.
Mm-hmm. Thank you. So we now move to the next one, and it is also regarding one of the architectures. So about event generation in LAR-TPC 2022. What are these generated images used for? How can we detect whether they are good or not? LAR-TCP 2022. Yes. What are the generated images used for, and how can we detect whether they are good or bad?
Okay, the data set that what using it was as a general uh, baseline for modeling, and another part was
Another part was how to know if those generated images turned out good or are they bad.
okay. If we are using GANs, so we compared the generating images and the dataset images.
I see. So there is some procedure to find out whether they are good or bad.
Yeah.
Great. Thank you very much. And from what I see, all other questions are more general, so maybe I can share my screen now. Thank you very much
Okay.
for
Was
returning to your slides. Yes, one tiny second for me to do so. Okay, so the question is it hard for ML engineer with weak knowledge of physics to contribute to such research?
actually it depends of previous your background, not only physics, but mostly in computer vision, as you can see, as for RTPC and their hits, and for Ice Cube with the domes, and for novas, we really have an images as input data. So if you have good knowledge in computer vision, and just to apply some new architecture, I think it can be possible.
Okay, thank you. We are moving to the next one. What is your experience using machine learning for neutrino physics?
We have published an article on open datasets, PillarNet, and we are trying to improve the labeling of Mitchell electrons, which are from the decay of muons. And we are trying to use self-attention block. But I can say that we have very good improvement in just a few percentages. But why Mitchell electron is so important? It's some candle in the neutrino physics for energy calibration and etc. So as we can do, we try to improve reconstruction of these Mitchell electrons.
Great. Thank you very much for the answer. And even achieving a couple percent of improvement, it's already a great achievement, because those are like there is that ceiling level in this area when the models are already good enough, but to make them even better, it takes a ton of work. So congratulations on that. Okay, we are moving on to the next one, the next question, which is, after lots of experiments conducted and processed using neural networks, do you still think it is a viable way to process physics data, considering that neural networks are poorly interpretable?
The one point that still is not hidden, but very difficult to calculate is uncertainties. Okay, if we can check by regular algorithms that interpretability, that okay, it's really good works, better than previous algorithms, not based on machine learning, but about uncertainties, I still have some questions for more experienced people in the computer vision. Okay, I can change for my own analysis. What I mean, in big experiments, there are groups which works just for all collaboration on machine learning algorithms, different. For example, at Dune, for near detector and far detector, it's different groups which are responsible to work on different algorithms. And we have different types of neural networks for all of these detectors. For near detector, it's mostly using for semantic segmentation. It's the same neural network as was shown for PillarNet, but now it's improvement have to be improved for the modulus of large TPC detectors, model 2 by 2. So we have 4 detectors within some spaces, and we need to improve all of these numbers for this compound of 4 detectors. And another one group for far detector was published a paper which mostly classification tasks. And now they are preparing another task already for regression, for neutrinos, energy, vertex position, and etc. And so on. But still, okay, yeah, it's still a question in uncertainty, according to this. Oh,
Oh, my microphone was off. Apologies. Misclick from
no,
me.
no, no. I just have read already the question.
Okay.
Okay. I will think about it, but mostly I have more experience on processing data which are already pre-processed in some kind. So I have already the energy of these hits and position. The waveforms I have never processes actually. So I do not have the answer on this question.
I see. And that's also like kind of more technical question. So later on with your experiments, you will try different things and we'll know for like what works better for you here regarding this. All right. So this was our last question for today. And this concludes the second lecture of the first day of our Cow Data Science School. Thank you very much, Dr. Gogota, for coming today and sharing your area with us. And I do hope that many of the participants listening right now who are not that much of the physicists themselves, but are more of like from the computer science background or machine learning engineering, that they will think about the possibilities that are really there for them to not be like concentrated on those areas that they are already familiar with, but also look up to other possibilities to apply their knowledge and their skills in completely different areas from nature sciences, in this case from neutrino physics, and also contribute to that kind of research themselves. All right, so once again, Dr. Gogota, thank you very much for coming. And
thank you for participation in your school.
Yes, so now we go on a tiny break because in 5 minutes there will be another talk by Mikhailo Koreshkov. And now I will pause the recording.